it's helpful to think about interference in terms of phase. And what we do here is we take that argument inside our sine wave and we just take that whole thing and simplify it down to one value that we're going to call phase. Make sure that you distinguish between phase and phase constant. We do use the same symbol, but usually we use a subscript on this one to distinguish it from that one. So that's going to be a little tricky here. Be careful with your notation. So when we're talking about interference, we're normally not worrying too much about time. We're going to be thinking about comparing two waves in the same moment in time. So really then it's just a question of what that x is, which can come from different locations. So different locations is going to impact that x. And then we can have different phase constants, which impacts our phase constant phi naught. So what that looks like if we just want to compare what phi naught is that if we have a snapshot graph, notice that both of these are for t equals 0, that if phi naught equals 0, then this looks like a sine curve, exactly what you expect. But if you have, for instance, pi over 2, well, what I like to do here is remember that this one whole wavelength corresponds to phi in terms of your phase. Sorry, corresponds to 2 pi. So here would be pi. So this first peak is at pi over 2. So if what you have is pi over 2, that corresponds to starting at a peak. Now you might also call this cosine. That's fine. That's in fact the phase difference between cosine and sine. So that's what we're doing with that phase constant. So another way that we talk about phase is if we have two peaks that line up, two waves are said to be in phase. And again, they might line up due to differences in both phase constants and position. So we have two different ways to think about changing this overall phase, but when we say in phase, we mean that this complete phase. So let's look a little more in detail at this. So phase difference is going to be this delta phi. And we're going to look at kind of some different delta phi's, which is going to make this confusing. So we have this delta phi and we have that delta phi. Notice that they're not the same. There is a subscript there that matters. So let's try to tease out what's happening here. We have two overall phases to think about. One that is coming from speaker 1, the second one coming from speaker 2. So notice that we're using subscripts on here to try to make it clear what each variable comes from. So the reason that this looks like phi sub 10, phi sub 20 is that this is our initial phase for speaker 1 and speaker 2. So that's why this has two subscripts. Remember that x1 and x2 corresponded to the distance between whatever point we're measuring it at, say there, maybe this is the detection point, that we actually then have for speaker 2, we would say this is x2, and we would say this is x1. So that's why we have x1 and x2 here. So if I then want to just look at what the phase difference is, not this phase, initial phase offset, but just the overall phase difference, all I have to do is subtract these two things. Well, notice that time falls out because these are going to share the same angular frequency because they have the same wavelength, they have the same wave speed, so those just cancel when you subtract them. But the other two values actually do propagate through since they're potentially different. So we're going to call this delta phi naught just the difference in initial phase. If we have identical sources, that means that the initial phase difference is 0. So this is kind of a definition to know. And what that means is just notice that if you have this equilibrium line here, that equilibrium line here, this looks like it has an initial phase offset of 0, and so does this one. That's all that means. We'll look at some examples where that's not necessarily the case. So this is true in general. This was a specific case, so this could be 0. But then what we do, remember that k is going to equal to 2 pi over lambda. And so that's how we actually get to from k to having 2 pi and lambda involved. So when we say delta x, that's just going to be x2 minus x1, and that's this path length difference. So that's the difference in placement between where speaker 2 is right up there, and speaker 1. So this is like saying what one speaker is 2 meters behind the other. So path length difference is something that's going to be really helpful to think about that comes into our interference equation very frequently. So now let's think about the conditions for constructive interference and destructive interference, and apologize for my notation mistake. So on the previous slide, we said that our change, our delta phi, our difference in phi, is given by this equation. So this is true in general. Then we can say, well, what is the condition for constructive interference versus destructive interference? And here I'm effectively saying perfectly constructive or perfectly destructive, though that is assuming that their amplitudes are the same as well. So if we want two things to line up, right? If we want a peak to line up with a peak, that would be our constructive interference case. So in that case, when do you have two peaks line up? Well, if you have a 2 pi integer phase difference between them, noticing that that can be 0. And so all that is thinking about the fact that this is what your sine wave looks like. If I have a sine wave that starts here, those look in phase, but that can actually be a 2 pi difference. It could also start another 2 pi later. So constructive interference is when the difference is 2 pi times an integer. Destructive interference is if you now start one here, right? That's your destructive interference. Or it could start here. Again, destructive interference. So this is now that 2 pi plus another pi, right? Where that pi gets you from being at where your sine is going up to where your sine is going down. So the takeaway here is that look for this, where whatever your path length difference and initial phase difference in this form gives you 2 pi times some integer, 0, 4, whatever, that's constructive. Destructive is when it's effectively 2 pi times m plus pi, or m plus 1/2 times 2 pi. So hopefully that makes some sense to you. Again, we're shifting things either in terms of initial phase or in terms of path length. So again, we'll look at an example of that in the next slide. Here are 3 different ways to get perfectly destructive interference. One is to actually have your 2 speakers in the exact same position. And again, we're thinking of this as a one-dimensional problem. We've just moved them vertically to be able to see better. And in this case, our delta x is 0. But our initial phase difference is pi. So one is initially going up, so that would be like the equivalent of 0 pi, and this one's going down, so that's a difference of pi. So when you add these together, you get 0. Now, we've actually separated them by half a wavelength. So their initial phase is the same. They share the same initial phase, so they're both going up. But now notice, if you kind of take this, that now when you sum them together, you're going to get 0, because if this goes up and then down and then up and then down, that's going to look like this when we put it up there. So in this case, our phases are the same, but we've shifted it by half a wavelength. So again, if you go back and plug that into the equation where you divide your delta x by the wavelength and m and factor in 2 pi, you see why this is going to give you m plus 1/2 times 2 pi. Now then, of course, there's 2 terms, so we can start to do something in between. In this case, they don't start at the same phase, and they have a different separation, but if we plug it into the equation, we actually see that this is going to again result in perfectly destructive interference. And again, if you just kind of look and say, okay, where does it start? It's starting there. That's my equilibrium line-ish, almost. It goes down, up, down. Again, you have that destructive interference. So keep in mind that there's 2 different ways to impact what our interference is, both position and then initial phase, and either one can cause constructive or destructive interference, but you do need to factor in both of them to understand interference.